Hi, everybody. It's Professor Mitchell. We are continuing with Chapter 9 on inferences from two samples. And today we are talking about dependent samples, also known as matched pairs. This section presents methods for testing hypotheses and constructing confidence intervals involving the mean of the differences of values from two populations that are dependent in the sense that the data consist of matched pairs. The pairs must be matched according to some relationship, such as before and after measurements from the same subjects or IQ scores of husbands and wives. When designing an experiment or planning an observational study, using dependent samples with matched pairs is generally better than using two independent samples when it makes sense to use matched pairs. It doesn't always. So the objectives in this section are to use the differences from two dependent samples or matched pairs to test a claim about the mean of the population of all such differences, and to use the differences from two dependent samples or matched pairs to construct a confidence interval estimate of the mean of the population of all such differences. The notation we'll be using in this section, D will stand for an individual difference between the two values in a single matched pair. Mu sub D will be the mean value of the differences for the population of all matched pairs. D bar will be the mean value of the differences for the paired sample data. S sub D will be the standard deviation of the differences for the paired sample data, and N will be the number of pairs of sample data. The requirements are that the sample data are dependent or matched pairs. The matched pairs are a simple random sample, and either or both of these conditions are satisfied. The number of pairs of sample data is large, as in greater than 30, or the pairs of values have differences that are from a population distribution that is approximately normal. So the test statistic that we'll be using in this section is from the student's t-distribution. It looks like this, kind of similar to one that we've used before. D bar minus mu sub D. Now, if we're doing a hypothesis test, this will be the hypothesized mean difference from the null hypothesis. Often it will be 0, but not always. Divided by S sub D over the square root of N. And as usual, we can use either the p-value approach, and remember that whenever we find p-values for a t-distribution, we have to use technology to get an exact p-value. If we use table A3, all we can get out of that is a range of p-values, which is usually good enough. Or we can use the critical value approach, and in that case, you can just use table A3. Notice that the degrees of freedom will be n minus 1. Remember, n is the number of pairs. Your confidence interval estimate for the population difference will be D bar plus or minus E. And this is how you calculate E. It's T sub alpha over 2 times S sub D over the square root of N. Very similar again to what we did when we were finding a confidence interval for a population mean with standard population standard deviation unknown. So back in section 8.3, I believe. And the degrees of freedom is n minus 1. All right, so the procedure is that first we're going to verify that the sample data consist of dependent samples or matched pairs, and verify that the requirements in the preceding slides are satisfied. Then find the difference D for each pair of sample values. Find the value of D bar and S sub D. So D bar and S sub D are the mean and the standard deviation of all these differences that you found in step 2. For hypothesis tests and confidence intervals, use the same t-test procedures used for a single population mean, again from section 8.3. Because the hypothesis test and confidence interval in this section use the same distribution and standard error, they are equivalent in the sense that they result in the same conclusions. So consequently, a null hypothesis that the mean difference equals 0 can be tested by determining whether the confidence interval includes 0. You've seen that a couple times before. All right, so here's an example. Data lists ages of actresses when they won Oscars in the category of Best Actress, along with the ages of actors when they won Oscars in the category of Best Actor. Now, what's going to make these match pairs is that this sample is taken from 5 particular years. So whatever year the Best Actress was 28 years old, the Best Actor was 62 years old. Okay. This is a small random selection of the available data so that we can better illustrate the procedures of this section. So this is a very small sample, but it'll be a pretty easy one because it's such a small sample. So we're going to use the sample data with a 0.05 significance level to test the claim that for the population of ages of Best Actresses and Best Actors, the differences have a mean less than 0. Now, I just want to point out, this is a one-tailed test because it says less than. So it is going to make a difference whether that means actress's age minus actor's age or the other way around, actor's age minus actress's age. All right, if I was looking at this slide and I hadn't read ahead, I would interpret the fact that they wrote Best Actresses first to mean actresses minus actors, okay? And also in this table, they've already calculated all the differences. So you can see right here, -34, that comes from 28 minus 62 and not 62 minus 28, okay? Okay, so requirement check, the samples are dependent because the values are matched by the year in which the awards were given. The pairs of data are randomly selected, so we will consider this data to be a simple random sample. Now, because the number of pairs is only n equals 5, we should check for normality of the differences and we should check for outliers, okay? And this comes back to, again, that section in chapter 6 that we didn't cover on assessing normality. So we'll just take their word for it that that population is approximately normal. All right, so step 1, we're going to look at the original claim. And the original claim was that the difference between actresses and actors' ages is less than 0. Okay, so mu sub d will stand for the population of differences of actress's age minus actor's age. That claim would be written as mu sub d is less than 0. And then in step 2, we write the opposite of that claim, which is that mu sub d is greater than or equal to 0. We take the one of those that does not contain equality, and that becomes the alternative hypothesis right here. And then the null hypothesis always gets an equal sign. So the null hypothesis will be that mu sub d equals 0. The significance level was given to be 0.05. The test statistic is going to be from the student's t-distribution. And now, before finding the value of the test statistic, we have to calculate d bar and s sub d. So using the differences that were given, and if I wasn't given these differences, I could easily calculate them, right? We find that d bar is negative 10.2 and s sub d is 14.7. Okay, so I thought it might not be a bad idea to bring up Excel because again, they really didn't have to give me those differences, right? I could easily calculate those myself. So suppose they had only given me the ages of the actresses and the actors, and I had to first find the difference. So that's super easy to do with Excel. Go to this cell right here, put an equal sign, and then select the first actress's age. Notice it puts an A2 right here, which means it's referring to cell A2. Then I'm going to say minus, and I'm going to select this cell, okay? There is a huge advantage to doing it this way instead of just typing equals 28 minus 62, and I'm gonna show that to you right now. So if I hit enter on this cell, it comes up with the negative 34, and even better, if I copy this cell and then tell it to paste it in all of these cells here, it will assume that I want to do the same thing in all those cells. In other words, do the first cell in that row minus the second cell in that row. It's really, really cool. So that's why it's better to use cell references than actual numbers. Okay? And as a reminder, to find the mean and the standard deviation, you go to any cell. I usually go to one at the bottom. Type equals average, and then select all of these cells. So there's that negative 10.2 they were talking about. And then for the sample standard deviation, type stdev.s and select all of these cells. All right, there it is, negative 10.2, and I think they said 14.7, right? Because they rounded it to 1 decimal place, okay? But when they do their calculations, I bet they're going to use the unrounded value. Using these sample statistics and the assumption from the null hypothesis that mu sub d equals 0, we can now find the value of the test statistic. The value of t equals negative 1.557 is obtained if unrounded values of d bar and s sub d are used, and technology will also provide a test statistic of t equals negative 1.557. Okay, and I just realized they wanted us to take their word for that on that t-score calculation. Let's not take their word for it. Let's actually do it. So here's the formula that we saw a little while ago, and I've written down the values of d bar, mu sub d, s sub d, and n. So upstairs we're going to have negative 10.2 minus 0, so I'll just write negative 10.2. Downstairs we're going to have 14.6526448, and I'm using the unrounded value so it doesn't throw off my t-score, divided by the square root of 5. Let me make it crystal clear that okay, main fraction bar is right there. So if we crunch those numbers, negative 10.2 divided by parentheses, 14.6526448 divided by the square root of 5, close, close. Okay, there's negative 1.55657, and they rounded it to negative 1.557. Okay. All right, so going back to the PowerPoint. Okay. So the p-value method, because we're using a t-distribution, we can either refer to table A3 for the row with 4 degrees of freedom, and we find that this test statistic corresponds to an area in one tail that is greater than 0.05. So if you're using the table, you would say that the p-value is greater than 0.05, or if you're using technology, that gives you a p-value of 0.0973. So let's check out both of those things. First, I'm going to bring up table A3. So here's 4 degrees of freedom. I am looking for the closest t-value to 1.557. Remember, there are no negative t-values in this table. Okay, so 1.557. Okay, I'm getting that that is between, and we're looking at area in one tail because this is a one-tail test. It's between 0.05 and 0.10. I think I would like to draw a picture of this for you. So let me bring my thing back up here. Okay. It would also help, of course, I can't see the table on my screen now, so let me see if I can dig it out of the book that I have in front of me. There we go, got it. Okay, so what this means, I feel like this is something I could say over and over again. We're looking at a t-distribution with 4 degrees of freedom. And we have found 2 t-values in the table. And I'm going to put them on the left side because we are looking at a left-tailed test. One of those values we're going to say is negative 1.533 out of the table. And that corresponds to an area in one tail of 0.10. So I'm going to put a 0.10 up here. Next to that, we have a t-value of, I'm going to call it negative 2.132. And that corresponds to an area in one tail of 0.05. Okay. So our calculated t-value is negative 1.557. Since that t-score lies between the 2 that are in the table, that means, and remember the p-value is this area here. So that means that my p-value is somewhere between 0.05 and 0.10. Okay. And that's the best we're going to do with the table. But the advantage of technology is that it will give you a more precise value. So let's look at that next. Okay, so I've got StatTrak just about ready to go here. I've gone ahead and typed in t-distribution calculator into Google. The first result is t-distribution calculator on StatTrak. So let's bring that up. Okay, so we're looking at t-score, 4 degrees of freedom. And I want to know what is the probability that t is less than or equal to negative 1.557. So when I hit calculate, it gives me a p-value of 0.0972, which is definitely between 0.05 and 0.10. I think it's a little off from the one that was in the PowerPoint because, probably because of rounding. Remember, we rounded this from negative 1.5565 something. Anyway, that's pretty close. Oh yeah, it's only off by 0.0001. So that's pretty good. All right. For the critical value method, we would go to table A3, 4 degrees of freedom, area in one tail 0.05, because that is our level of significance. And we would find, well, the table would give me a 2.132. It would not have the negative sign on it. So you do have to be careful and adjust it for when you're doing a left tail test. So here's the critical value of negative 2.132. So the green shaded area is our critical region. If my calculated test statistic had come out anywhere in that region, we would reject the null hypothesis. Because my calculated test statistic is up here, this is going to be a fail to reject. And by the way, that's the same conclusion that I would get with the p-value approach. Remember, when p is high, the null will fly. So the p-value is higher than alpha, which means fail to reject the null hypothesis. So that means that there is not sufficient evidence to support the claim that the mean difference in ages is less than 0. In other words, there is not sufficient evidence to conclude that best actresses are generally younger than best actors. All right, so now to find a confidence interval for that population mean difference, we're going to construct a 90% confidence interval estimate of mu sub d, which is the mean of the age differences. And remember, by using a confidence level of 90%, we get a result that could be used for that previous hypothesis test, because it's a one-tailed test with a significance level alpha equals 0.05. The confidence level should be 90%. And we've talked about that once or twice before, but let me just scribble a picture here for you. So here is my t distribution. Here's area in one tail equal to 0.05. That means the area in the right tail also has to be 0.05. And that's why the area in the middle would be 90%. Okay. All right, so moving right along. Yeah, there we go. All right. Okay. The solution for the previous example includes verification that the requirements are satisfied, so we don't have to do that again. Here they're showing me a stat disk display that just generates the 90% confidence interval. We're going to do it with the formula on the next slide. Okay. So notice that the 90% confidence interval puts the population mean difference between negative 24.2 years and positive 3.8 years. Okay. All right, if you're doing it with the formula, it would look like this. T sub alpha over 2, which is obtained from table A3, is 2.132. S sub D is 14.7. We got that from Excel earlier. Divided by the square root of 5, that comes out to 14.0158, something, something. So that is our margin of error. So now we take our sample mean difference, which is negative 10.2, and we plus or minus the 14.0158, blah, blah, blah. And when you round those values to one decimal place, they're rounding them to one decimal place because that's one more than was in the original sample data, right? Those ages were whole numbers. You get that we're 90% confident that the population mean difference is between negative 24.2 years and positive 3.8 years. All right. So in the long run, 90% of such samples will lead to confidence interval limits that actually do contain the true population mean of the differences. This confidence interval does include the value 0. So it is possible that the mean of the differences is equal to 0. And that indicates that there is no significant difference between ages of best actresses and best actors. And that's the end of section 9.3.